Good morning. This is your 8th digital class for the subject physics. Now, in last class we discussed about Gauss's theorem. Now, in this class today we are going to discuss the application of Gauss's theorem. Now, before starting the application, let me define once again the Gauss's theorem. Now, what is Gauss's theorem? It says the total electric flux through any closed surface is 1 by epsilon times the charge enclosed by the surface. Now, to define the total electric flux through any closed surface, what we used to do, we used basically closed integral. So, the symbol for closed integral already we have defined. The symbol is your this symbol basically. This is the symbol for closed integration over the closed surface. So, integration over the closed surface is denoted by this one. So, this symbol you are going to use in Gauss's theorem. So, the Gauss's theorem is closed integral E vector dot ds vector. This is your electric flux. The electric flux through any closed surface is 1 by epsilon times the charge enclosed by the surface. Now let me try to go for the first application, that is electric field intensity due to an infinitely long uniformly charged wire. So this is your infinitely long uniform charged wire, positively charged wire. Now we have to define field intensity at P. Now to define field intensity at P, what we have to do, we have to construct a Gaussian surface. Now this is your Gaussian surface. Now this Gaussian surface is in cylindrical in shape because the line charge is basically cylindrical in nature. So before going to the details, let me define Gaussian surface. This is your Gaussian surface. Now what is Gaussian surface? I have given here note. Please check it out. Gaussian surface, it is an imaginary closed surface such that the intensity of electric field at all points on the surface is same. So this is your Gaussian surface. So field intensity at this point is same because this is your wire. So the distance of this surface from the wire is nothing but the radius of the cylinder. You can say radius of the cylindrical Gaussian surface, and here to here the distance is fixed, and here to here is also the distance is fixed. As the distance is fixed, the field intensity can be defined E equal to kq by r square. So r is fixed, which is nothing but the radius. So that's why the field intensity remain same on this surface, curved surface of the cylinder. So this is your Gauss's theorem. Now what we have to do, we have to split this integral in parts, because you do have three closed surface here. One is your top, another one is your bottom, and third one is your curved. So we have split this integration, which is nothing but the integration over the closed surface, in three different parts, because you do have three closed surfaces in this Gaussian surface. So this Gaussian surface encloses charge, which is nothing but the length of the charged wire L, and rest part is out of this Gaussian surface. So the charge enclosed in the Gaussian surface is nothing but the charge available over the length L of the wire. So if we consider if lambda be the charge per unit length, then your total charge is nothing but is your Q equal to lambda L. Q is nothing but the charge enclosed by this Gaussian surface. So how much charge it enclosed? It is the charge enclosed is nothing but is your lambda L. Now at P we have to define the field intensity. So what we have to do, we have to consider a small element at P, and which we have defined as ds. Now the direction of this ds is normal to this surface, as we have defined in last class the area vector. If you have to define the direction of the area vector, what you have to do, you have to draw a normal. So ds direction is along the direction of the field, because it's positive charge, so field is outward. So E and ds is in same direction at the point P. But if you consider the top as well as bottom, the small element ds, the direction is in up, direction is in down, but the field is in this direction. So field and ds, that is the area vector, is in perpendicular. So if we consider 1 and 2, integration over the closed surface 1 and 2, you will see that this goes to 0 because E is perpendicular to ds. Now what we will do, we will impose 3 and 2 in 1. So if we impose 3 and 2 in 1, we will get this expression. So what you have to do, you just practice on the copy during the watching of this video, so that simultaneously you can go for the mathematical part. So this is your ultimate equation. Now on the surface 3, E and ds is in same direction, so E ds cos 0 degree lambda L epsilon naught. So E is constant on this surface as the definition of the Gaussian surface defined. So E comes out from the integration sign and integration 3 ds. I have not used this small circle over this part of the integral because as I have space 3, so 3 is nothing but the closed surface. No, already it is closed, so I have not used this symbol here. You can use the symbol, no problem, and in some book the symbol is also available in the integration, but if you don't give the symbol then also it works. So ds is nothing but is your area of the curved surface, which is nothing but 2 pi rl. R is the radius of the cylinder and L is the length of the cylinder. So if you simplify it, E comes out to be your E equal to lambda by 2 pi epsilon naught r. So this is very important expression for the field intensity at any point near the infinitely long charged wire. So what it says, all part is constant, so E proportional to 1 by r. So if you go for the graph, the graph is like this, because if r is less, E will be high. So r is less here, so E will be high. As r increases, E decreases, because it is inversely proportional. So this is one application of Gauss's theorem to define the field intensity due to infinitely long uniformly charged wire. Now let us go for another one, electric field intensity due to uniformly charged infinite plane sheet. So this is your plane sheet, and the charge available is your plus charge, positive charge. Now what we have to do, we have to define field intensity at this point as well as at this point. So what we have to do, we have to extract a small portion from this infinitely uniformly charged plane sheet. So this is a small portion we have extracted. I have given a figure here. You see, this is your plane sheet. So it is a charged. So we are not going to use all the charges. We have extracted a small portion of this plane sheet, and considering this small portion, we have constructed Gaussian surface. We have constructed Gaussian surface. Now this small portion has an surface area S, and this small portion has a surface area S. So this is your Gaussian surface. So this is S, and that further small element of this surface S is your ds. So this part we are using here in the diagram. So this is your plane sheet. We have extracted a small portion of area S, and considering that as your base area, we construct a cylinder of a certain length. At where we have to define the field intensity. At this point we have to define the field intensity as well as we have to define the field intensity at here. Now as per the Gauss's theorem, this is your Gauss's theorem. Now out of the small s, we have considered a further smaller element ds at this point as well as at this point. So ds, E vector is outward, here is also E vector is outward, ds is up. So ds is up and E vector is this side, so ultimately the dot product of ds and E on the curved surface goes to 0. Only these two parts will survive. So again we have split up this integral, closed integral, 1 this end, 2 this end, and third the curved one. So as the charge resides inside the Gaussian surface is nothing but the charge available in the small element of area S. So if sigma be the charge per unit area, then charge available inside the surface S is your Q equal to sigma S. And for the third one, E perpendicular to ds, that's why it goes off. Now 1 and 2 we have to use. Now 1 and 2, ds and E is in same direction, so it goes your cos 0 further comes out, and E comes out because E is constant, and ds is nothing but is your S, so ES and 2ES, E equal to, further simplification, sigma by 2 epsilon naught. So electric field intensity depends on the surface charge density. So here once again I am repeating, this small s we have considered a part of this plane sheet, and the charge resides on the small s is nothing but is your charge available inside the Gaussian surface, and further from the small s we have considered a small element ds. So if you integrate ds, you will get s, which we have got here. ds is your s. So this is second application. Now this part you see, we have just used this part here under the note. So instead of taking one sheet, we have taken two sheet, and charge density is sufficient sigma 1 and sigma 2. So we have split the region 1, 2 and 3. Now we are going to use this expression which we define in single one, that is your sigma by 2 epsilon naught. Now in the region 1, as it is positive charge, field will be outward for sigma 1 e1 vector, and for e2 for sigma 2 also there is a field, that is your e2, that is outward, that is towards the negative x-axis, you can say. And on the region 3 you do have e1 and e2, both e1 is for this sigma 1 and e2 is for this sigma 1. So you do have positive x-axis direction, and in between the sheet, e1 for sigma 1 is your this side and e2 is sigma 1 for this side. So you are going to use this expression in vector notation. Now in region 1 you see this region, basically e1 and e2 is in negative x-axis, so negative I cap is the direction. So sigma 1 by 2 epsilon naught negative I cap, here is a negative I cap. So if you sum up the total field, then it goes to your sigma 1 plus sigma 2 to epsilon naught I cap with the negative sign. In region 2, e1 is this side, so it is your positive I, and e2 is this side, so it is your negative I. So if you sum it up, you will get sigma 1 minus sigma 2 to epsilon naught I cap. Similarly, in region 3, e2 is in this side and e1, so both are in positive I cap because in positive x-axis. So e1 equals sigma 1 by 2 epsilon naught I cap, sigma 2 by 2 epsilon naught I cap for e2. So if you sum it up, you will get sigma 1 plus sigma 2 by 2 epsilon naught I cap. This is your 2 epsilon naught. If sigma 1, this is your field for two different infinitely charged plane sheet, infinitely thin basically. If sigma 1 equal to sigma, this condition we have considered, and sigma 2 is your minus sigma. If one is your plus sigma, another one is your minus sigma, how do the field changes? Then region 1 goes to 0, sigma 1 minus sigma, sigma minus sigma goes to 0. Region 2 is your sigma by epsilon naught. This part we are going to use it later on. If you substitute it here, sigma 1 sigma, sigma 2 minus sigma, so minus minus plus, it becomes sigma by epsilon naught. These are the magnitude part we are considering. And region 3, again it goes to 0. So this is all about your field intensity. Now already you have used the symbol integration over the closed surface, Gaussian surface, and imaginary closed surface, such that the intensity of electric field at all points on the surface is same. So these are the notes. Now these are very important because in every alternate year, even in continuous year, this application used to come, and this comes under the 5 marks. So in exam it is used to ask that state Gauss's theorem and find the field intensity due to infinitely charged, infinitely long uniformly charged wire, or uniformly charged infinite plane sheet. You do have two more application. One is your shell, another one is your charged sphere. So out of these 4 application, definitely you will get one application in your exam. So this is very important topic, and probably in next class we are going to complete this first chapter. So please go through this topic very thoroughly and apply this formula for the numericals, because numericals though you will try here, but as more as you can try, it becomes more clear, concept becomes more clear. So this is all about your 8 digital class for the subject physics, and next class we are going to discuss 2 more application of Gauss's theorem and few numericals, and after that we will go to the next chapter. Okay. Thank you.